Hello, everyone. Welcome. I've gotten this question a couple times, just that we're not doing Lab 7 today. Lab 7 will be Thursday. We are still on our Thursday labs, but we are going to do things. We are going to get through a good amount of the sources of magnetic fields. I am very glad you all are here because teaching right-hand rule is so difficult not in person. Oh my gosh. Even my lecture class, it's very hard to teach. Even in that class for people that are in person, it's such a physical thing. And we got another right-hand rule to learn today. Maybe 1.5, depending on your perspective. One's a shortcut. So I am glad you all are here because that means I can actually help you with like physically moving like your hand and stuff like that. It makes such a big difference. Anywho, all right, we'll do the joke and then I'll go through a bunch of logistics.
Hello, everyone. Today's joke. I bought the world's worst thesaurus yesterday. Not only is it terrible, it's terrible.
If you haven't used a thesaurus, it's a book of synonyms. You may or may not have used a thesaurus in your life. That's like, my generation was the one that was on the, like, before the internet, kind of, sort of. Anywho. All right. Some logistics things for you all. So I sent out a couple of announcements between Thursday and today. One of them was that the free response grades are posted. Pretty happy with how things went. I was a bit more like unsure right after the test, but after grading them, I was really, really happy that people largely had a sense of what to do. And that's really all you needed to do to get a good amount of points on it was if you wrote down what variable you're solving for and you have a picture, that gets you like 2 or 3 points. If you then identified the right equation, that basically gets you to 50% of the points just from those things. And then anything after that is execution of the process. So, all that to say, pretty happy with it. Yeah, and we're going to have the exact same kind of format for test 2. With the caveat, one modification I'm going to make to test 2 is your all's first test had 3 questions, each with 2 parts. The next test is just going to be, I don't know how many questions. It may be 5 or 6 still, but you'll just choose. So maybe it'll be 6 questions, but they're all independent of each other. So it's 6 separate, instead of like an A and a B, it'll just be like problem 1, 2, 3, 4, 5, 6. Pick 4 of them. These were all, you were kind of locked in. Whichever one you picked, you had to pick A and B. But they were all independent in terms of solving. This one, they'll just all be fully independent, and you'll choose 4 out of the 6. So that's kind of my current plans for this upcoming test. You'll still be solving the same amount of problems. They just won't be kind of tied together. That's the only modification. All right, there's that. Something I sent out to you all is I sent you all a announcement regarding an Excel spreadsheet. So there's a couple grading things that I do in this class which cannot be displayed in web courses. There is no way to like quote unquote program them into web courses. They're things I have to do. And with that in mind, it can be kind of tricky then to determine maybe what your grade is with these. So I made this Excel/Google, it's Google Sheets, but you can download it as Excel. Grade calculator. So it makes you make a copy so that you can actually edit it and it doesn't mess with the master file. Same way you'll do lab reports. And so this is what it looks like if you haven't opened it. All the red boxes are the boxes that you fill in. So it's all the various grade categories in this class. We have the labs, we have the iClicker, we have the quizzes, we have the AI professional readiness. That we're going to talk about the AI assignment. I did finish that and post that. Test 1 total, test 2 total. And then there's another red box here for your final. So the red boxes are the only places that you type in. Everything else you don't want to touch. You're going to break things. So what you do is you put your percentage. Say you did every single lab and you got 100% of the points there. Great, I put 100%. Maybe you got 85% of the iClicker points. The quizzes, let's just say you did most of 90%. Let's say you did, I'm just making up numbers here, 90% on the career whatever thing. Test 1, let's say you got a 60%. Test 2, let's say you got a 75%. Great. What does it do for you? It calculates your grade Here, I'm going to stay in the zoomed out way just so you can see everything all together. I know it's smaller font. It calculates your current grade with I know it says Top Hat. Pretend like it says iClicker. I just realized that typo now. It calculates your current grade with and without iClicker. Whichever one's higher, that's kind of like your current grade in the class. Then, below this, it shows your score, your overall score in the course. It's very low right now because the final hasn't happened. The final score is not in here. So you give a hypothetical. If you're like, hey, what if I scored a 70 on the final? You type in 70, and then it spits out what your final grade in the class would be given all these grades. Now, I just want to point out a few things. Again, it does the with and without iClickers, and then it takes the higher of the two. So this one, the with iClickers was higher, so it kept that one. What it also does is notice that test 1 was a 60, but down here, test 1 shows as a 70. Why? It's because it replaced it with that 70. The final still counts as a 70. You can see that over here. The final is 70. But remember, one of my course policies is the final will replace your lowest test grade if it is higher. Your final will replace the lowest test grade if it's higher. What if it's not higher? Let's say, for example, you scored a 50 on the final. 50 is smaller than 60. Then neither of your test grades get affected. And you can see that in the document. So, play around with this if you want to. This is just to help you all keep track of your grade in the course using the two things that I can't put in web courses. It's a tool for you if you want it. So that's one thing that is made. The other thing is, whatever, give up on that. I made the AI assignment, so I already chatted about this a bit, but I'm just going to kind of remind you all and show you what the assignment actually looks like. So there's assignment on top of all the professional development things of hopefully you all were able to get involved in some club or research or something. If you weren't already, if you were, great. If you weren't, hopefully you were able to do something. The last one of those will be due October 25th, and that's just, hey, did you do it? If so, how'd it go? If you didn't do it, what's your plan moving forward so that you're a marketable person? Because remember, if you just do your classes, you will not stand out. Because everyone does their classes. What makes you stand out compared to other people when you apply for a job? It's going to be these outside of class experiences. That's just the reality. And there's things you're going to learn in it that will be invaluable to you. All right. So this assignment, very straightforward. You're like, oh, another assignment. This is probably something you're kind of already doing. My goal is just to help you do it more effectively. So this is using AI effectively in problem solving. Whether you like it or not, too much money is being invested in AI for us not to realize it's probably going to be important and a skill that you all need. Just like when the internet came out, if you knew how to use it, you're at an advantage. Just like when the computer came out, if you know how to use it, you're at an advantage. If you don't know how to use it, it doesn't mean you can't get a job, but it does mean that you're going to be less marketable, less efficient, less effective. That's my perspective on it. That is what lots of people with lots of money also believe. So, anyhow, this little guide is how to use it effectively. Something I wrote up based on my experiences of working with students. The whole goal of this is that to support you all in using AI in much the same way I engage with students. So the levels of kind of learning are kind of represented here, and I applied it specifically to AI. The first level, and I use the car analogy. When you're trying to learn how to drive a car, one of the first things you do is watch someone drive a car. But that is a very passive way of learning. At no point are you actually physically touching the car in any way or engaging with the car in any way. And there is value to this passive learning. You learn that you learn about the pieces of the car. You learn about the steering wheel, where the stick shift is, things like that. Facts, just straight up facts. Do you actually know how to use them? You might think you do, but if you remember back to the first time you drove a car, it's a vastly different experience than watching someone drive a car. The same is true of everything in your life, as far as watching someone do it versus doing it yourself. Great, passive. It has its uses, but it doesn't really have any depth, and you're just getting facts and information, not how to apply it. Surface level is kind of the next one. You're in the car. You might ask some questions. There is some engagement. There is some higher level. You're actually kind of looking at it, asking maybe a little bit of questions, but it's still fairly surface level. You still are not actually engaging with the task itself, in this case, driving the car. What I want to get you all to, what I want to help you all with is being active. Yeah. Oh, it should be. Something's on. Something's streaming. All right, let's check real quick. It might be mislabeled because I keep making that mistake. But if you go to my YouTube channel, Wesley James, yeah, it's just called Lecture for reasons that aren't clear. Anywho, oops, it's called the wrong name, but it's there. I'll rename it later. That's not very helpful for the people online. But if you want to text them just to search my name on it, it'll work. All right. But yeah, thank you for letting me know that. All right. I want to get you on the third level where you're actually doing it. This is where when you all first drove the car for the first time, you're kind of in the car, you're holding it. And I think of this, we think of AI as a machine, because it is. This is like lane assist, cruise control. It will do a lot of the work for you, but you are still actually holding the steering wheel, still engaged with it. You are doing something active. You are participating in the process in an active way. It's still doing a good amount, maybe an okay amount of the work, but you're working with it. That's where we want to be. That's the learning thing. Your hands are on the steering wheel, or in your all's case, your hands are holding a pencil. You're actually physically solving problems at some point. Now, how do you actually then use it in an active way? These other two levels require kind of mastery of the topic. You can check this out if you want, but we're just focusing on the third level. How do you make it active? You give it the problem you're working on, but you don't just copy and paste the problem and hit enter. That is the most common way people use AI to solve problems. Take the problem, put it in there, hit enter, see what it spits out. That's passive. It's doing everything. You didn't really do anything in that process. How do you make it an active process? You actually work on the problem, you give it the problem, and you send it a picture of your work. Or you tell it, I tried solving it this way, but it didn't work out. Why? You give it information about what you have done. Or you have it ask a guided inquiry. Someone did tell me that ChatGPT does have like a study mode where it actually does ask questions as opposed to just giving you the answers. And so there is some of these baked into some of these models currently. I can't speak to the other ones. Anyway, active, engaging. You are actually at some point solving things. You're writing stuff down and using it as a tool, as an assistant, not as doing all the work. Make sure you do provide the question that's clear. It will make assumptions if you don't. Ask follow-up questions. Why did you do this step? What if I did this instead? Hey, I used this method instead of the method that you did. Is that wrong? Is that right? Why? And then you need to make sure the answer is right. It makes as many mistakes currently kind of as I do. Roughly, that's been my experience. Awesome, great. All right, this whole guide exists, and then your assignment is very straightforward on this, and it's just graded on whether or not you did it. What was the initial prompt you gave it? That could be the question, but it needs to be with some follow-up. If you just gave it the question and hit enter, it's just going to spit out the whole thing, and it's passive. You just watch someone else do the whole thing. What initial prompt did you give it? Ideally, this has some kind of, hey, what if I did this way? Or maybe you put a picture, yada, yada. And then basically, it's a conversation after that. This is something that's new about this compared to Google. Google, you could put a problem in it, and you had a very high chance of probably finding that problem online somewhere or something like it. The thing that's new about these large language modules is you can actually have a conversation. So what was your first follow-up question to it? That could be, why did you do this? What if I did this instead? Hey, I did this step. Is this correct? Why? Why not? Why can't I do this step if it tells you no? What's your second follow-up question? What's your third follow-up question? Multiple follow-ups here. Engaging. Active. It's not a one and hit enter, because that is often how people use these things, and that is a very shallow use case of this. And then, did you find it useful? Yay or nay? Why? And then you just copy and paste your entire log below, and that's it. This is a skill you have to practice. Doing these follow-up things is a skill. So I'll give you all an example of how I used this last night. And it was, the end result didn't work out well, but it's not the large language model's fault. I was trying to fix my fridge. My fridge stopped working. Specifically, the freezer side was working, but the fridge side wasn't. So what did I do? I gave it the information of the problem. I said, hey, freezer side's working, this isn't working. What are some troubleshooting steps I can do? It then gave me some troubleshooting steps. And then I went through those and I said, hey, it maybe said, check this, check this, check this. So I checked those things. I physically had to do it. It can't do it for me. It can't see my fridge. I checked each of those components. Realized that my back panel maybe was it wasn't thawing correctly or something like that. The airflow wasn't great. Cool. So last night I took it off, blew dry it all off. Then it wouldn't turn on afterwards. Very sad for me. Found out that I didn't connect the ground cable back somewhere, and it might have fried things. I had to buy a new fridge. It's very sad. Now, did it steer me wrong? No, actually, it was a mistake I made. I didn't connect the cable. It didn't know I disconnected this cable unless I told it. But all that to show is an ongoing process. Hey, I tried this. It gives suggestions. I implement those things. I say, hey, I don't think that's a good suggestion because of X, Y, Z reason. It's like, oh, I didn't know that information. Great. I'll reevaluate. Active. I now very well understand how a fridge works and the inner workings of a fridge. I know what to do next time. But yeah, this is super practical for so many things. So great. This is due next Saturday, but it very much is a do it, submit it, you get the points. The purpose of this, though, is to try to build those skills with you all because it is, I genuinely believe, a skill that you have to like anything you're doing. And this is applicable to every single one of your classes. And it's, we'll see if it's the future. I'm not really a betting man, but I would. A lot of people are, and they're betting a lot of money on this. A lot of, gosh, so much money. All right. Anywho, source of magnetic fields. New stuff. Yay. My monologue is pretty much over. So, let's start doing this. Things you need to remember. Vectors, cross products. Current is defined as positive charge moving. Magnetic fields. Forces due to magnetic fields. Stuff we've been doing. Okay. What are we going to cover in this PowerPoint? We are going to cover how to calculate the magnetic field due to a current carrying wire. Specifically, there's only 3 geometries we're going to be looking at. And if we want to make a more complex system, we're just going to put a bunch of them together. We're going to find the magnetic field due to an arc of wire. I know I put here loop of wire. A loop is just a completed arc. So we're going to figure out magnetic field due to an arc of wire. Whether that's a full loop, half loop, quarter loop, something in between, great. We're going to figure it out. We're going to find it due to a straight wire. And we're going to figure it out due to something called a solenoid. A solenoid is basically a slinky. That's the best way I can describe it. A spring slinky, that's kind of what a solenoid is. It's a bunch of loops, 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 loops. We'll see it when we see it. And then we're going to use Ampere's law. Ampere's law is the magnetic field version of Gauss's law. So, the benefit of this is you're going to get to use the same skills that you developed for Gauss's law. If you didn't develop the skills for Gauss's law, you're going to get extra practice because it's going to use very similar principles. There's really only like a couple scenarios we can use Ampere's law for, much like Gauss's law. There's actually less scenarios for Ampere's law. But this will be good practice for us. This is really going to test if you can do that current enclosed. It's going to help us practice that skill more than anything else. Previously it was charge enclosed, it'll be current enclosed. All right. This question I was very surprised about in my lecture class when I asked it, so I'm going to be curious how it goes here. What generates electric fields? And what experiences a force due to electric fields? So this is from test 1. This is not a new thing, but we're going to use this idea of what makes a field and what experiences a field to understand the new things. So is it mass that experiences a field and experiences a force due to a field and makes a field? Is it moving charges that make electric fields and experience a force due to electric fields? Is it stationary charges that make electric fields and experience a force due to electric fields? Or does everything experience this?
Yeah,
I know, that's all like, yeah, that's all I actually I don't know if It's a weird. I think they do. I think they do as well. Yeah, and that's kind of what I was just. I just know that. Depending on your reference, feels different than so I don't know when that.
It says they do.
They should. I mean, it's on radio. It's on radio signals, are they?
Oh yeah.
You got an oscillating charge.
What?
That part's not
Yeah, I know.
What do you think?
I don't like that. Also, solve conditions. Sometimes you have. I have the bad one. Yeah.
Exactly. All right, give y'all like 20 more seconds. And this one I'm purposely like not walking around as much because I want to see how it is a bit more without influence. The answers are surprising. All right, we'll close this one in 5, 4, 3, 2, 1. So the answers here are surprising to me. I didn't expect this, but that's what one of the probably makes it a really good question to ask. All right. Something that's very helpful with this is to write the equations for these things. Why? The equations are a succinct representation of logic and the concept. They're like as succinct as you can put it. That's why equations are so useful. Remember, math is a language. An equation is a sentence. As weird as that sounds. If I want the force due to an electric field, well, there's a couple ways I can write this. So what makes a experience of force due to an electric field? Let's actually just write this one. Q times E. That's the, what's the force? It's Q times E. Q is charge, E is the electric field. All right, but what makes an electric field? Well, we have an equation for that. KQ over R squared. Electric fields are made by charges. Charges make electric fields. Now, the answers here are very surprising. So I got some C's, I got some D's. Not everything has charge. There's 3 fundamental particles. Protons, neutrons, and electrons. Neutrons are neutral. They do not make an electric field, nor do they experience one. And actually, if you have a whole conglomeration of charges, if I have equal positives and equal negatives, my net charge is 0. Most objects are uncharged. This desk right now, I guess you could maybe say there's a very, it's basically making no electric field because it's basically uncharged. So yeah, this is a good question. Now, I will give it to moving charges. Technically, as long as you got charge, whether or not it's moving or not, you still get an electric field. But yeah. There's plenty of objects. I mean, most things in this room are uncharged. Their net charge is 0. So they are not generating an electric field. And yeah, neutrons is the easier example to give. All right, on to the next question. What generates magnetic fields? The whole goal here is the things that make a field experience a force due to that field. The things that make a field experience a force due to the same field. So what makes magnetic fields? Hint, it's the thing that experiences a force due to a magnetic field. Is it moving charges, mass, stationary charges, or moving objects with mass? This one I'll go around and check as well. And when I go around, be prepared to have, if you have an equation for it. Nothing easy, but it's useful. It's a good review. Let's see.
The first thing I wrote.
No, I don't.
Yeah.
All right, give y'all 20 more seconds. All right, in 5, 4, 3, 2, 1. Yeah, so this comes from last week, and we're going to use the equation because the equation represents It's a nice sentence for us. So what's the magnetic force equation? It's QV cross B. Or we can rewrite that in the way that we actually use it in this class to avoid the cross product. QVB sine theta. You need all those things. B is magnetic field, so you need that for magnetic force. And you need a charge, and that charge needs to be moving. If any of those terms are 0, Q, V, or B, there is no magnetic force. So, moving charges. If it's stationary, V is 0. If I have mass, but no charge, then Q is 0. And, yeah, who cares if the object's moving if it doesn't have charge? Great. Fantastic. So what's the big summary with all this? The things that make a field experience a force due to said field. That's the big idea here. That's one of the common threads that we've been seeing. What makes a gravitational force? What experiences a gravitational field? Mass. What makes a gravitational field? Mass. What experiences an electric field? Charge. What makes an electric field? Charge. What experiences a force due to a magnetic field? Moving charge. What makes a magnetic field? Moving charge. The things that make a field experience a field. Newton's third law. Every force equal opposite, all that good stuff. All right. Now, on to the new right-hand rule, which is why I'm very thankful you all are here, because these things are a pain to teach remotely. New right-hand rule. The last right-hand rule, let me just make sure we remember. The last right-hand rule was to find force on a moving charge. Keep that in somewhere in your brain. Right-hand rule number 1 was to find force on a moving charge. Right-hand rule number 2 is to find the field due to moving charges. First one finds force. Second one finds the field due to a moving charge. So I'm going to give it to you all in 2 ways. The first one is, in my opinion, a bit more conceptually rich. You'll see it gives you a better overall picture. The second way is more straightforward and just kind of gets you the answer. Both are fine. Neither one is bad. So, rule. Moving charges make a magnetic field. Specifically, they make a magnetic field that's a circle around the moving charge. You can almost think of it like it's orbiting it. It's not actually, nothing is actually orbiting it. The field around a moving charge looks like a circle. That's just a rule. That's an observation. How is that proven? If you take like a current-carrying wire and you sprinkle some like iron shavings around it, you'll see some circles. You can experimentally observe this very easily. Make circles. How do we find the direction of these circles? Thumb in the direction of current, and then your fingers kind of make this like arcing, this circle kind of path. So you can see here in this picture, I've got a current-carrying wire. I stick my thumb up, that's the direction of current, and you can see my fingers kind of make a circular kind of thing. They make these circles. If I want to find the field at any point, let's pick a random spot on this picture. Say I want to find the field right here, some point to the left of it. The direction of the field is tangent to that circle. It's a line that's tangent to that circle. All these circles are made up of a bunch of arrows strung together. Which way does the circle point here? It points kind of outwards, if you think of this three-dimensionally. This arrow points outwards. So if you kind of put your thumb up at this point on the circle, the magnetic field points outward. What if instead we pick some point in front of it? Again, imagine again the circle's kind of going around. Which way does the circle point here? To the right. Which way does the circle point on this side? This is not an arrow that's upward. These are a pain in the butt to draw. 3 dimensions is a pain in the butt to draw. This is not an arrow up. This is an arrow into the page. And on the back end, we get a magnetic field there. So you all can hopefully, pick any point and you draw a tangent. This is the direction of the magnetic field at a bunch of random spots. Just random spots I picked. Okay? If I want the field at any particular spot, I pick that spot, I draw the arrow, great. But what's key here is it's making kind of this circle. Yeah. What if you're at the end of the wire, like past it? That's a good question. It will do some weird bending, kind of. It's more complicated. Yeah, you won't have to deal with the end of a wire. The question was, what if you're at the end of a wire? If you're kind of past it, it's going to do some funkier kind of shit. It still very likely will make that circular, but it might do some other weird things. The symmetry, I think it will still make circles. All right. So that's one way of doing it. And if you kind of look here, you can see the in and out. The key here is imagining that there's like this circle going around it. And how do you determine this circle is orbiting the wire? Again, it's very hard to draw these things. It's very hard to draw three-dimensional stuff, which is why I appreciate you all being here in person so I can work with you all. This is one way of doing it. I'm now going to show you all. This way kind of gives you what the whole field looks like. And if you want a specific spot, pick that spot, make an arrow that points tangent to the circle. Let me now tell you the more I'm going to call it the blunt way of doing it. So I'm going to copy this exact slide. Your thumb is still going to point in the direction of current. So point thumb in the direction of current and have your hand flat. So, you make that L-shaped thing. The next step, point fingers towards the place where you want to find the field while keeping hand flat. So I'm going to apply, so you do this, you pick the point. So in this case, my current carrying wire is up. So I put my thumb up. I then point my fingers towards the place I want to find the field. Say I want to find the field on this left side here where it says B. I want to find it here on this side. So I put my thumb up. I point my fingers there. Which way does the field point? The direction of my palm. Points out of the page. So that's the other way that's kind of more blunt. It gives you the exact spot. Your palm points in the direction of B. Palm points in the direction of the magnetic field. This method works, but it only gives you at one point, whereas when you kind of do this rotating thing, you get kind of all the points, and you get a better, fuller picture. But both work. All right. I got 4 practice ones here, then we'll do a clicker one to see how much it made sense. So let's just look at this left side. Find the direction of the field at point A and point B. You got options. You can do the whole, put your thumb in the direction of current and imagine a circle that's kind of going around it and find the field at point A and find the field at point B based on that circle. Or you can do the thumb in the direction, point your hand up, and your palm points in the direction of the field, or thumb direction. Try it out for a bit, and then we'll walk through it. We'll go around and work with you all. Yeah. That's the same reason I do the curl. And it's the physicist because it gives you the whole picture. It's the same reason you do the curl as the swing. Gives this more matches. But I realized I needed the other method. I'm biased. Both are good.
So obviously, because I only use switching it to yes. Can you send it to me? Can I add you? What? Can I add you on
Yeah, make sure you use your right hand. Use your left hand is that. Right hand moves. You only got 2 minutes.
Oh wait, right. Oh, okay. Especially making it harder for myself, but I know we said, are you trying?
I know you're right. Yeah.
I know that I was curious. I know it's like,
Yeah. All these are fine. Yeah. So someone decides to push her this way, and they see the right rule, right hand rule, this current defined in this way. Because even these directions of the field is arbitrary. The fact that we decide to make it this way or this way, someone just decides. Because we do want to iron filings around it. They don't have to. They just line up. You can see a circle, and we just decide to do this. Alright, so there's the answers for the first one. You know, again, if you imagine a circle going around this, at the top that circle goes into it, and on the bottom that circle goes out of it. You can figure out the way the circle's rotating using that right hand rule and your fingers and all that jazz. Otherwise, you do the, just line up your fingers with it, and that method also works. You do the same thing on this one, and we get a magnetic field on this side that points into it, and this side that points out of it. This is something you got to physically do it. Trying to do this in your head is not a good idea. As evident, specifically, I'm speaking from me right now. Anytime I do these problems, if I try to do it in my head, I got a very high chance of messing it up. It's really hard to hold 3D stuff in your head. So to try to hold that the direction of current is this way, and then imagining your hand making, it's just a lot to imagine. So don't try to imagine all of it. Just make your hand do this, and then it does a lot of the work for you. That's why writing stuff down is always good. It'd be really nice to draw a picture, but oh my gosh, it's so hard to draw. Look, here's a circle that's going around it. It's either a circle going around it or an oval that's it's very difficult to draw these things and have them actually represent what they're supposed to. This is why we use the X's and dots. But when we draw a plane on it, that helps. So that's why there's this plane here. So I have a current carrying wire going upwards. And I have a point that's in front of the wire, kind of out of the page a little bit. Find the magnetic field at this point P, this point that's kind of between you and the wire. Is the magnetic field at this point towards the wire, away from the wire, left or right? Let's see how this goes. I'm optimistic.
Well, I guess if you have the vectors, yeah. So your problem is
You want to do this one, Tyler? All right, 10 more seconds.
It's very strange. So your thumb's the direction of the current. You point your fingers towards the points in front of it, and then your palm.
I thought you were doing this.
It is. Not the answer.
Okay, that's what.
No. The point is out of the
So it looks like my advisor
Good.
And that's just good because you can also just see if you imagine that circle going around. You can imagine your fingers at that point. It will always, that's why we use this rule. His fingers give you the direction. If it was upside down. Yeah, that's we know it's going to make a circle. This helps you direct it. That's the only way. Otherwise, I like to know this circle. Think we always have on two. That's how it be. Alright, go for it.
All right. So for this one, we can see that our current is going up. So we're going to point our thumb straight up in the direction of the current. And you can do it the two ways. You can either curl your fingers inward, and then at the point P, which is in front of you, you can see that your fingers are pointing to the right. Also, if you're able to, I couldn't do it easily with the flat hand, point it straight at you. You can see that your palm's facing to the right. So either way, you'll see that the magnetic field is going this way. So the answer is D, to the right.
Great. Yeah. And again, I keep harping on this circle thing. Again, if you're able to get the direction, that's fantastic. The reason I keep mentioning a circle thing is that is the nature of all magnetic fields make a circle. And this is something you've been seeing your entire life. You all have seen magnetic field. You've seen pictures of magnetic fields. If you're like, I haven't seen that. Let's look at the Earth real quick. The Earth makes a magnetic field, and you all have very likely seen this picture somewhere in your class. Oh my gosh, what are these shapes? They're kind of like circles. Now if you're like, but wait, where's the current? Inside the center of the Earth is a iron, maybe molten, maybe solid. Which one is it? Is it solid? I think they think it's solid, right? The center of the Earth, iron core.
Yeah.
Solid iron core. It's really charged. It's a charged iron sphere that's spinning. Oh, a bunch of charge making a circle, that's current. And we're going to learn how to find the magnetic field to a loop, but it makes this. So this is one example. All magnetic field lines loop back on themselves. Always. Every magnetic field line loops back on itself. There is no such thing as, we call it a monopole, which is something that makes a magnetic field where it doesn't loop back on itself. Let's look at a magnet. Oh, look, there's one. They just modeled the Earth as a magnet. Oh my gosh, what are these magnetic? They're circles. We're going to model the center of the Earth as a loop of wire. Kind of, sort of, we're going to do it. But I just want to show you that all magnetic field lines are circles. So this whole circle thing is something that you've seen before. Now we're just drawing the circles. And we're specifically doing it with current-carrying wires. Anyway, we'll get to loop. All right. To prepare you for this next slide is going to say Biot-Savart law. And then it's going to show us an integral that's going to look a little intimidating, let's call it. I don't know. Maybe it doesn't look intimidating. It tends to throw people off. You will not be solving this integral. you will actually not use this equation at all in this class. I will not give you a problem in this class where you will use this equation. However, we need this equation to make the equations we will use. Okay? So the slide I'm about to show you, you're not going to use that equation in this class. If you're a physics major, you will do this at some point. You will derive the equations we're going to do later on. But we need to know, this is the law. This is the observation of reality. This equation I'm about to show you is determined by experiments. We're going to then use it to derive the expressions we're actually going to use. Okay? Why am I not going to have you use this to solve things? Because there's only 2 scenarios that we're actually going to use it for. And so I'm just going to give you a solution to those 2 scenarios and call it good. That's how it pans out. All right, facts about law. This is the law. This is how you calculate the magnetic field due to a current carrying wire. Mu naught over 4 pi times I dl cross r over r squared. And the cross product just turns into I dl sine theta over r squared. Mu naught is a new variable for us. It's a constant. It's 4 pi times 10 to the minus 7. It's called the permeability of free space. If you all remember way back, we did epsilon naught before. Epsilon naught is the permeativity. It's a very subtle difference. One's got a B in it, one doesn't. The one with a B in it's for magnetic field. That's kind of how I remember it. Permeability, it's got it, whatever. They're different numbers. So permittivity of free space, permeability of free space. The value for mu naught is 4 pi times 10 to the minus 7. It's a constant. It will always be that, assuming we're in a vacuum, which we will be. If you all remember, epsilon naught was 8.854 times 10 to the minus 12. It's just a constant. Constant. It's a constant. You just plug it in. All right. We are now going to apply this equation to find the magnetic field due to an arc of wire. And it's a very simple derivation. It is one that every single person in this room, I'm fairly confident, would be able to do. You might be intimidated by it at first. We're going to use this equation that might look a little rough, but we've been practicing integrals, and it's not going to be bad. We're going to use the same tricks we've been using the entire class to set up these integrals. So, all right, here it is. This is what we're going to derive. We're going to do it together, and I'm actually going to have you do some of the steps because you can, because you're capable. So, we got our picture. Remember the way we set up integrals is we tend to draw little bits of the kind of wire. So we draw little tiny DLs. And we're going to find the magnetic field at that point P. That's the goal. Now, first step I want you all to practice, and this is going to be relevant for a later clicker question. I want you all to find the direction of the magnetic field at that point. I drew 2 different quote-unquote wires, DL1 and DL2. They're just little tiny pieces of wire. Find the direction of the field here. Let's call it DB1. What direction is it? Find the direction of the field here, DB2. Do the right-hand rule that we just learned. Practice it. Try it. Which way does the field point to each of those tiny little pieces? All right, I'm going to walk over to one of the boards. So y'all tell me at point P, we're going to do it, let's just do it the quick way. I point my thumb in the direction of the current. I point my fingers at the point. Which way does the field point? Out of the page. Great. What if I do the second point? Which way does the field point there? Still out of the page. Oh, look, everywhere on here it points. That's really convenient because all the fields are going to just add. They all point in the same direction, so we can just add them up. We don't have to worry about components or any of that nonsense. Great. Remember, that was always how we start these problems. We pick 2 tiny little pieces. We see what they do. Next step, we write the integral. My integral is going to be the integral of mu naught I over 4 pi. All I'm doing is copying this down. Here, I'll even write it exactly the same. I'll put the I over here. It's the exact same thing. I'm not doing anything new. Magnitude of I, magnitude of DL, sine of theta over r squared. Let's now look at each piece of this. Mu naught is a constant. 4 pi is a constant. I is a constant. What can I do with that? If they're all constants and have an integral, what can I do? Pull them out. Mu naught I over 4 pi. There's another variable in here that's a constant. There's actually a couple. But we're going to get to them in just a second. We'll do one step at a time. We just picked our first terms. Let's look at the next term, dl. I have an arc. Anytime we have an arc, what do we turn dl into? We've done this a bunch of times now. R d theta. We've done this a bunch of times. We're going to do the same thing here. Anytime you all have an arc of wire, it gets turned into r d theta. Great. We'll plug that in just a second. This sine of theta, this is the angle between r and dl. It's the angle between r and dl. Why? It comes from the cross product. Okay? Let's look at our picture here. Look, they drew a random r and they drew a random dl. What was the angle between that one? 90. Great. Let's draw another r on this other dl. Oh my gosh, what's that angle? Oh, how nice. What about this one? Oh my gosh, they're all 90. Just plug in 90 into the angle. Boom, this angle is 90. Why? Because the picture says so. Pick a bunch of random points, you can see it's 90. Great. This r is the distance from the wire to the point. Look, I got one r here. I got another r here. I got another r here. How do they all compare? They're all constants. Guess what we can do? Pull it out of the integral. Hopefully you all are seeing how easy this is. So I'm going to pull that r squared out. Sine of 90 is just 1. So what am I integrating? R d theta. But what did we just say r was? Constant. So we get mu naught I times r over 4 pi r squared. One of the r's cancels. We are now integrating over d theta. What is the integral of d theta? So easy. Like, super easy integral, y'all. So, boom. That's the answer. That's the solution for the magnetic field due to an arc of wire. Mu naught I theta over 4 pi r. Mu naught is a constant. I is the current. Theta is the angle. You can see it in my picture here. It's the angle of this arc. Whatever that angle might be. We're going to practice a problem to see if you can figure out what theta is for a specific scenario. Very important. This theta is in radians. Very, very, very important that you put this angle in radians. Why? This arc length requires you to be in radians. Angle degrees are made up. Why are there 360 degrees in a circle? Because some human decided there was. Arbitrarily. They may have had a reason, but it was just an arbitrary reason. Radians are real. Radians are real, meaning they're from the universe. There is a ratio between the circumference of a wire and its radius. What is that ratio? 2 pi. How do you go from radius to circumference? 2 pi r. If you want half of a thing, it's pi. Pi is not something someone decided. It is something someone measured. They took a loop of wire, wrapped it around a circle, measured the length of it, and when you divide it by the radius, it spits out 2 pi. You can do that yourself. It's experimentally determined. So, great. There's it in writing. There's the equation. You have to use radians. If you put in degrees, it's nonsense. Putting in degrees is like you just decided to multiply by a random number because 360 degrees is made up. Pi, 2 pi, pi over 2, those are experimentally determined things. All right, so let's see if we're paying attention on this, and I'm going to make up some answers. I'm going to change these last 2 answers on purpose. Does that mean they're right? Does that mean they're wrong? What a great question for you to figure out. But this is to make the point clear. So, my question is, what is the magnitude of the magnetic field at the center of a half circle of wire? And I'm going to put the original equation here, just since it's the first time we've seen it. I'll put it up here for you. This is the equation we just derived. What is the magnitude of the magnetic field at the center of a half circle of wire with radius r and current I? I have to give you those as givens. Is it, I know these are kind of all crammed together. Yeah, it'll be okay. 2 mu naught I over pi r, mu naught I over 4r, mu naught I over 4 pi r, mu naught I over 4 pi times 90, mu naught I over 4 pi times 180. I'm seeing if I can give you all a little bit more room so they're not running into each other and really hard to read. 1.5 is way too much. Yeah, that's fine. That's better in its own way. All right. Try it out. Work together. There's only one right answer here.
Quick question. So earlier when we were discussing epsilon.
Yeah, I don't think I'm taking anything.
Yeah, permeability is used for fields. And conceptually, the way I understand it is this is how easy or difficult it is to make a magnetic fast. Permittivity is how easy or difficult it is to make a electric issues. These values change as we go through. So, one's for magnetic fields, one's for electric fields.
Okay, but they like
And then what's really weird is you take that one, and you divide it, I believe you take that, divide by epsilon naught, and you get yeah, and that's going to be, because light is an electric and
Yeah, I mean, you only need statics for the Catholic.
oh,
Don't take my spot. I will gatekeep it. You're certified.
it's 1 over the square root.
Well, you might just get
of them multiplied.
You're certified.
Yeah, but it still comes, yeah. This one, if you multiply them together, 1 divided by the square root of that. Yeah, but it's because together they make one. Light is magnetic and electric.
Make sure you get
Alright, what did y'all get? One. Oh, yeah. I don't think I wrote that through.
Wait, really? Yeah, we want to go like that.
And that's why you always
Yeah, I feel like that might. I think you have
it's unfortunate to see. That's why I purposely didn't write the data and signed it in the same line for that reason. It would have been better if I put that. Yeah, no, that's a great point. I appreciate the thought. In fact, I'm just going all that. All right, give y'all 10 more seconds. I think we're looking pretty good here. All right, in 5, 4, 3, 2, 1. All right, so doing this equation, you just plug in the variable. So B equals mu naught is still mu naught. What's my current in this problem? It is I. It says so. 4 is still 4. Pi is still pi. What's the distance from my wire to the point? That's R. That's the radius of it. The only question is what's theta? And if it's a half circle, that's pi. Pi's cancel. You get this answer here. Looks pretty good. I think most people got that. the last two answers that I chose to just chuck in there, they're wrong for two reasons. One, they use degrees, which is nonsense. Degrees are made up. And they're also missing the radius on the bottom, too. They're wrong for two reasons. But yes, please be careful. There's a reason why when you get to your upper level kind of courses, eventually, things like default to radians, like when you do stuff in Google, when you do stuff in coding, the default is radians. Degrees are nicer in terms of understanding, because if I told you 0.0567 radians, you have no idea what that, I have no idea what that is. My brain can't, I'd have to convert that to pi, a multiple of pi, it's gross. If I told you 30 degrees, you have a visualization. So we use degrees because it's easier for our brains to make sense of, but radians are what mathematically actually have meaning. They're the real quote unquote thing. They're at least from reality, measurements, yada yada. All right, great. We have already practiced this one in some way. That was actually how we started our derivation. So let's see if you can do it. What is the direction of the magnetic field at the center of this half circle of wire with radius r? You found the value. Now find the direction. This is something very important in these weeks, is can you find directions of things?
They like really. Well, if you just take your finger and curl it, where the they really stick away. Yeah.
The new flow chart, or the old flow chart now, you have to take some vibrations. For the new flow chart, you can take those separate. You should. Vibrations you control is really hard. They're pretty manageable when they're separate forces. And control and vibration counts as one of those advanced items you have to take. So you're killing two birds with Yes, so I'm not going to do it. I'm not actually saving any credit hours. I'd rather just take the vibrations and controls together and suffer and having to take a break. No, he's priced at the regular. No, it is. What do you mean? Look at the 20. There's this guy who has like 10 speakers.
Oh, everyone's all right, 10 more seconds because I think we're looking pretty good. All right, in 5, 4, 3, 2, 1. All right, so right hand rule, you put your thumb you basically just pick any part of this wire. You can pick a whole bunch of points if you want, but pick any point. The current does this counterclockwise thing. And as your thumb kind of goes around it, your palm always points outward. So we get a field that points out of the page dead center. Now, what happens everywhere else? What does the field look like everywhere else? So So we're going to see it in just a second. I just want to draw the picture. So what happens here? We just did this one. If you all do this one again, this one is like rotated. Again, it's really tricky to draw these. So what's happening here? If I pick a little piece here, it's kind of out of the page. Here it's this way. Here it's to the left. So in this one, here's what the field does. The field does a big old circle on this side. On this side, it does a circle like this. And everywhere kind of in between, the lines always should be connecting. Boom, boom. That's the wrong direction. You got to be really careful with these things. You get all these circles. Because remember, when we're doing that the right-hand rule, you're getting all these circles revolving around it. So each of these loops makes a little circle around it. And the combination of all those circles, you get this big field. What does this look like? It looks like the Earth's magnetic field. Look at that. Except this one's opposite, but it's fine. So, the Earth, why does it make a magnetic field? Because at the center of the Earth is a bunch of charge going in a circle, just like a loop of wire. How is that charge going in a circle? It's an iron core that's charged, spinning. A spinning iron sphere has a bunch of, you can imagine it like a bunch of loops of wire spinning around, charge spinning in a bunch of circles. And you get this strong field. If that core ever stops spinning, that was the premise of the movie, The Core. What a movie. If you're familiar with it, if not, gosh, I watched it when I was real young. The core of the Earth stopped spinning and the Earth's magnetic field stopped. And they had to tunnel down to the middle of the Earth and then they reset the spinning by detonating a bunch of nuclear bombs. You know, it's classic Sci-Fi Channel, sci-fi movie. But this is why other planets maybe don't have magnetic fields, is they don't have this spinning core. These cores do slow down as time goes on. Why? Gosh, I have no clue. I can guess. You know, they interact with the sun makes a magnetic field that interacts with ours, and all these kind of complex mechanisms. It's not a simple thing. Something really crazy about the Earth's magnetic field. It has been well proven that I say well proven. There is evidence, very strong evidence, that this flips. That the Earth's magnetic field flips every random number, and it's not consistent. I don't know, Angelina, if you know more about this than I do.
We have a good estimate. It's not like consistent, like exactly, but
So when's the next? Do you have any?
like several thousand, maybe millions of years.
Hopefully, it'd be very bad because when it flips, things don't get deviated. The magnetic field of the Earth. Remember we talked about what do magnetic fields do? They cause forces on moving charges. What moving charges are important to us? The sun, the solar wind is a bunch of really high energy moving charges. And if they hit us, it's very bad for you. If you think UV rays are bad, these charged particles are way worse. Very high energy, very destructive. They are deviated by this Earth's magnetic field. They're kind of trapped in it. They get cycled in, or they get kind of... Because these Earth's magnetic fields, you show them all as circles here. The Earth's magnetic field actually stretches. So this is a better image of the Earth's magnetic field. It actually is squished on one end and stretched on the other because there's charged particles and they each make their own magnetic field and yada, yada, yada. But fun things. Long story short, the Earth is just in the middle is just a coil of wire. Loop of wire. Bunch of loops. All right. I am now going to teach you right-hand rule 2.5. You don't need to know this, but it's a nice shortcut, if you can remember it. It's super... Look, you're going to be thankful for this one because it's a shortcut. If I want to find the magnetic field in the center of a loop, ready for how easy this is? Curl your fingers in the direction of the loop and your thumb gives you the magnetic field in the middle. So if you want the magnetic field in the middle of this wire, just make your fingers match the coil. Which way does your thumb point? So if I match this picture, the magnetic field inside of this points inwards. Super easy. This is a shortcut for loops. If you ever have loops, just take your fingers, curl them along the current. Boom, my thumb points inward. That's the direction of the magnetic field. This is a nice little shortcut if you have a loop of wire. You don't need to find like every single element and then do the thing. You can just whoop, thumb points in, done. It's a nice shortcut. That's why I call it right-hand rule 2.5, because it's kind of like a shortcut for right-hand rule 2 if you have a loop of wire. not like its own rule per se. And this works for a square loop, this works for a circle loop, this works for a rectangle. If it's a loop of wire doing any kind of crazy thing, this will follow that rule. All right. Cool. Okay. We're going to do this problem and then we'll take a break because this closes out the arc of wire, and then we'll do the straight wire after the break. We will finish early today because I don't want to get too far ahead of my lecture class. We're already pretty ahead. But yeah, okay, so looking at this picture, this might look really, maybe this looks intimidating to you. Let's figure out what we're doing. What is the magnetic field at point P due to the current and the wire shown below? So I have this kind of funky looking wire here. And the key to any problem is to break it into pieces that we know what to do with. So I want to see if you all can break, you need to break this into 4 pieces of wire. 4 shapes, 4 simple shapes. And remember, the only shapes we care about are arcs and straight wires. So break it into 4 pieces. That's the first step. Color code it if you want.
Into the page, yeah.
All right, so what are my 4 shapes here? What 4 pieces am I going to break this into? 2 arcs and a straight side. I'm going to color code them as different colors just so we can see that there's 4 pieces here. You're going to see my ability to trace things is not great on the screen. Great, there's 1 arc. There's another piece. And then we got a piece down here, a straight wire. And then we have a piece down here. That's a straight wire. Now, these straight wires, remember, what does the magnetic field look like around a straight wire? What do all magnetic field lines look like around wires? It's a circle. The magnetic field around this wire makes a circle. Circle. Does it ever really intersect that point P? No. So what is the contribution? Basically, if we can break this into 4 pieces, if we can find the field due to each piece, you just, then add them together. So let's label this. I'm going to pick the easy ones first. So we'll call that wire 1, wire 2. I'm just going in order. Wire 3, wire 4. The contribution of the field, and then if we want the net field, B net is going to be the field due to each of these added together. Remember, we can only add vectors if they are parallel or anti-parallel. We are blessed in this problem that they are. But yeah, what's the field due to wire 1? 0. What's the field at that point due to wire 3? So find the other 2 and make sure you know the direction of them. If they go the same direction, add them together. If they go opposite directions, you better subtract them. They're vectors, they're arrows. Figure it out. I believe in you. You've done 1 arc, just now do 2. Oh, and make sure you tell me the total direction of the field at the end. I want the amount and the direction.
That's right.
Send it with that difference. I find out the page as positive.
Yeah.
So then, it'll still be
Yeah.
Or
Because A will be smaller than B.
yeah. When A is smaller than B, the contribution for A.
The field will be stronger due to wire A because it's a closer distance.
Correct.
So 1 over A
Oh,
So-
fractions. Yeah.
will give you a bigger number.
Right. Okay.
Yep.
I'm trying to figure out.
It's not that hard.
Yeah, because the fact that they're opposite directions, they're probably going to this one's going one way, this one's going the other. So how do we figure that out? Two, that's the base line. Whereas this one, I trade. So this one went this way. This means the leg was really well. Or if we use the right hand rule 2.5, we can just. Yeah. I get the total force would be, or the total field would be, but distance was B minus F.
Yeah.
So rule of thumb, if you're looking at something where the two finding one the other, they're going to be opposite. So is that it? You can't do that. I can't do that. Yeah, I just put it up like yeah, it's, you got options. You can do the right hand rule too. Oh, wait. You got. I had to. Now I'm on this side of it. So that's just move your paper. And why I say that because it's easier. If this is on this side of my body, it's really like if I put your paper over here, it's really awkward for me to do that. The other way is you can just do this whatever you want. If you do the right hand rule 2.5, this way it points down. Right hand rule 2.5 is like works. It works for any. If it's a part of a loop, yeah. Yeah, any kind of piece of a loop works.
All right, so hopefully the first step is finding the directions of these fields. You need to know which way they point. Which way does the field point due to wire 4? It points out of the page. Why? Right hand rule 2.5 is the easiest way to show it. You just curl your fingers along that and your thumb points out. And then the right hand rule 4 or the 2, that one's going to point into the page. Why does this matter? One's in, one's out. So they're not, you got to pick a direction. I'm just going to keep, for moving forward, I'm going to call out of the page positive, into the page negative, because I think that is probably what most people would want it to be. So we get B4 is positive, B2 is negative. So we're going to get B2 plus B4. Then we just remember the equation for a arc of wire is mu naught I over 4 pi r times theta. Both of these are half loops, so theta is just going to be pi in both cases. So we do mu naught I over 4 pi. Wire 2 has a distance of b and an angle of pi. There's a negative sign. Don't want to lose that. Plus mu naught I. The other one also has pi. That one's 4 pi times a. Pi's cancel. And I get mu naught I. I'm going to pull out my constants because I don't want to keep writing them. Negative 1 over b plus 1 over a. Now, that equation is not going to tell you the direction. That equation will not tell you the direction because we don't know the values of a and b. But you all can figure out the direction. Which one's going to make a stronger field? The one that's a smaller circle and closer to the point, or the one that's a bigger circle and farther from the point? The closer you are, the stronger the field. That will be true of that will be true of coil. That will be true of loops of wire. That will be true of straight wires. Solenoids are kind of like our capacitors where distance won't matter. We'll see that when we see that. But that rule generally holds for pretty much the closer you are, the stronger the field. So this is going to be out of the page guaranteed. I don't care what the values of A and B are. A is always going to be smaller. If you divide by a small number, you get a bigger number. Mathematically, you can figure that out. So, even without any numbers, you can predict the direction of this. All right, we'll go ahead and take a breather. We're going to kind of derive, after this, we'll derive the straight wire, practice it a little bit, and then after that, we'll be done. We're not going to go too much further today. Straight wire is much worse. It's not. It's the integral.
Are you doing infinite?
Yeah. Oh no, finite.
Finite.
I'm gonna give them the expression of finite because if you have a finite, you can do infinite.
Oh, I see the.
Yeah, I looked at that slide and I was like, I do not miss that again.
It's all just doing the integral. Getting to the integral is not bad. And honestly, I'm not even solving it. I'm gonna say I'm gonna solve it. You can look at this, but it's just not worth. All it does is get people. I think a lot of people.
Too much work.
Physics majors should do that. Even in their class.
They're gonna do that.
I hate to say that. Yeah. Yeah. Like, I think enough of all the courses, it makes sense to
My partial differential equation class, we just assumed like this really obscure trig identity. I actually like completely forgot. Like I have to learn that again.
Cosine 2 theta, sine 2 theta, and the cosine squared there's a y. It's really bad when at some point in my grad class, they were like, the solution to this integral is the gamma function.
Oh, gamma function is crazy.
It's just like, what the hell is that? Gamma function. It's a function made up to solve the integral.
One of my classes right now, we're talking about well, we did like expect comments, like how like we can practically like quantify the volatile and we just the zeroth order vector function of the second time.
That's the kind of stuff you know, like.
That's why I'm like, sci-fi dot. Like, we're coding this. This is not real math.
Yep. Yeah, the American calculations are good enough.
That's what most courses is heading to anyway.
I
don't know. People enjoy it.
That's what I like.
You like
That's why I do the. That's why I'm not.
The other one I ran into was quantum grad quantum is he was like, oh yeah, this integral is solving this complex plane.
Yeah, the Laplace transform.
No, it was something like trace something around it in the residual.
Oh, we were just talking about residual.
Like, what are you talking about?
Yeah.
Complex plane. It's just one of those I did. No clue what's going on anymore.
need to do that for a project I'm working on right now. Yeah. We'll see.
I just had to look it up.
I just have to like. For me, it's just an type code. The computer needs to know the math.
So you're
No, I'm working with No, I didn't want to
okay. Nice. Well, I was surprised. I didn't realize that they're doing this. My experience with I was surprised. They do all
let's go data a lot of times, but like the science is if the data's not enough.
We were just working with my numerical records to use the data from the Cassini mission.
All right. Straight wire. Straight wire. We're gonna go through, and the integral is gonna require trig sub, so we're just gonna kind of skate past that. We're going to set up the integral, and then I'm going to say, here's how you would solve it if we wanted to spend the time to do trig sub. But we're not going to do the trig sub because I don't want to. So great. Okay. This picture is the key to doing this integral. Just like every integral we've ever done, we need to draw a picture. So in fact, I'm actually going to get rid of this picture. So I'm going to make a new, oh, where'd it go? I got rid of it, but didn't get rid of it. All right. So I'm going to do a new slide. We're going to build the picture together because there is something important in this picture. Boop, boop, boop. There it is. Now it's gone. All right. Magnetic field due to a finite wire. This is the second system we need to find the magnetic field due to. Remember, it's arc of wire, straight wire, and then solenoid. Those are the three systems we care about. All right. Finite wire, not infinite. So I want to find the magnetic field at some point B. How are we going to do this? The same way we've been doing every integration problem. If I want to find this, I need to break it into pieces. So I'm going to draw a couple small pieces. So I'm going to draw a little DL here. I'll draw like another DL here. It's beneficial to have a couple of them. Now I'm just going to, same thing we did with charges. We're going to draw the line from that little piece to the point I'm trying to find the field. What do we label this distance as? R, right? You know what's also helpful in this picture? So draw this angle here. We've done that in the past. It's still going to be useful. Now, something weird. So we're going to do the same thing over here. And we're going to do something that's going to be maybe a little odd. Remember, I'm taking this arm, and I'm going to have to, it's easier just to physically show this. For me to sweep across this, I'm drawing this here, and I'm like sweeping this R kind of across the thing. As I go along the wire, and I pick different pieces, my arm is showing different R's. Why does that matter? If we look at this angle, we're going to use this angle. Because that angle came from, it's the same angle. As I move my arm along it, this angle down here still is this angle, still is this angle, still is this angle, still is this angle. So we're using the same angle kind of in every piece. This is going to be important to the derivation. So, call that theta 2, call that theta 1. It's the same angle, it's just at a different, my arm is at a different thing. So we call this like R1, call this R2. Great. Now, we do need to find the direction of the field. So I'm going to let you all try that. Go ahead, see if you can figure out the direction of the field due to each of these pieces. Remember, it's just making those circles. Even though it's like off axis, don't worry about that. Do the exact same process. Pretend like that point was directly above it. So spend a few seconds. Find the direction of the field. The current here is going to the right. What is the direction of the field at this point, P, due to each of these pieces? Pretend like this point was directly above each of these pieces. It accomplishes the same goal. So, if we pretended like that point was directly above it, which way would the field point above it? Out. Which way does this one? Same thing, it's out. Yay, it's in the same direction. Why is that good for us? They just add. That's nice for us. We don't have to worry about any funkiness. So this one is out of the page. Let's call this DB1. This one's out of the page. Let's call this DB2. All right. Now, I want to integrate over the... Okay, so I got my equation here. Yay. Make it a little smaller, make it easier to move around. My only goal here is to build the integral. This is something you all can do. You all are very capable of building this integral. Equals the integral of mu naught. Okay, look, let's just pull it out. It's a constant. Hopefully we're cool with that. Hopefully we're cool. I is a constant. Mu naught is a constant. 4 pi is a constant. So just pull them out to the front so I don't have to keep writing them in the integral. Remember that this cross product is the same thing as dl cross r, which is the value of just r, over r squared, sine theta. Remember that cross product is written as the multiplication between the magnitude of the terms. The magnitude of r hat is 1. R hat is called a unit vector. Its value of 1. It points in the direction of r, whatever. All right. Questions for you all. Which way is my wire? DL. What do you think we're going to replace DL with if my wire goes left, right? DX. If I want to integrate over the wire, replace DL with DX. Why? Because my wire goes, left, right. Hopefully not a big intuitive jump. DX. It's what you want it to be. Sine of theta is the angle between R and DL. Oh, look, it's labeled in our picture. That's useful later on. In fact, we can actually, and this is some distance. What are we going to call this? D? D. Sure. It's some distance away from the wire. So what does sine theta equal? We've done a triangle. Sine of theta equals adjacent over hypotenuse. We do need to define our coordinate system here. Let's just call this 0, 0. Why is that convenient? What's the distance from here to here? It's just x. Though that gets grosser as you get along the thing. Where is it easier for us to define our coordinate system? Let's call this 0, 0. That's a little bit nicer for us. Why is that nicer for us? What's the side of this triangle? X. The distance from there to DL. Great. This is going to be, we didn't even need this. D over R. Why? Sine of theta equals opposite over hypotenuse. Hopefully everyone's cool. We've been using these tricks. So, D over R. What does R equal? R equals the square root of x squared plus d squared. Why? Because triangles. You do not need to know any of this derivation, by the way. I'm just doing this to show you it's not out of thin air. Mu naught I over 4 pi. And then we're going to have the integral of d over r cubed, which is going to be x squared plus d squared to the 3 halves, dx. And there's another d in front of it, which kind of looks funky. It's fine. D is just that distance. Great. Oh, look, trig sum. Are we going to do it? No. No, I don't want to. What's the length of this? From some distance, L, negative L, to whatever it is on the right side, the whole wire. Great. If you really, really are like, man, I sure really want to do the trig sum, there it is. It exists. It's fine. I need to double, triple check because I got an extra factor of R. Oh, here the sine theta hadn't gotten swapped out yet. That's why.
Does the there's no need to break into components because the field doesn't break left and right.
Yeah, it's a great question. There's no need to break this into components because they all point out. All right, looking at this, what do we care about? The final answer. Great, there's the equation for it. So after doing trig sum, interesting enough, it gets left in these thetas. That's why we put them there in the first place. So the thing that you all need to know is how to use this equation. So the equation here is mu naught I over 4 pi r, which looks a lot similar to one that we saw before. But instead of multiplying by theta, we multiply by cosine of theta 1. This is theta 1 down here. It's the angle from the leftmost part. And theta 2. What is theta 2? Theta 2 is this angle, the one that we drew on our picture. It is not this angle. That is not theta 2. Theta 2 is that bigger angle over there. Okay? All you all need to know when it comes to this equation is basically what the thetas correspond to. The r is the distance from the shortest distance to the point. Yeah. No, it does not need. This is anywhere along the wire. This is anywhere along the wire. That is a very important observation because the problems I'm giving you will not be dead center. But this is nice. This equation gives you every single point, every point. In fact, this will give you the magnetic field at some point over here. Off the wire too. In that case, theta 1 is going to be this angle. Theta 2 is going to be that angle. You just draw the angles on there. You just need to know what those angles represent and how to draw them. But it's literally any point in space. Yep. It's great. This formula is on the formula sheet. The one for the arc of wire is on the formula sheet. So moving forward, it's just how to apply these. You do not need to be able to derive them, but you do need to know what these angles correspond to, because that is not drawn on the formula sheet. And when I mentioned theta and the arc one, you need to know what that angle represents as well. All right. Yeah.
So is this saying like it's the integral, so it's like the continuous effect of the magnetic field, right?
So that, yeah, it was
like one endpoint to the other endpoint.
So the integral was to give us the magnetic field due to all these infinitely. We basically take this long piece of wire, we imagine it as an infinite amount of tiny pieces of wire. We find the magnetic field due to every tiny little piece, and integrating it gives us this equation.
Okay, so like
Yeah.
theta 1 and theta 2 represents
Those are set. No, those are set. This is a finite wire where theta 1 is based on, you draw this picture. Yeah. Theta 1 and theta 2 are actual angles. They are set angles. How do you determine them? Based on the picture, based on the problem. So, all right. Let's see. We're going to then take this and make the infinite wire. With the finite wire, it should turn into an infinite wire when we take the two ends and we move them to infinitely far away. So my question to you is, what is theta 1 if I take that left piece of the wire and I stretch it infinitely far away? Obviously, I can't draw that, so let's exaggerate it. Take this piece of the wire and make it, whoa, off the page. Keep going. What is theta 1 as I approach infinity? What happens to this angle as I approach infinity? As I go farther and farther and farther and farther and farther, does that angle get bigger, smaller? It does approach a value. What value is that? And we're going to work in radians because.
I think it's E.
Because it gets fluxed. Yeah. And then we'll do the other
It's
side.
hard to think about it.
Yeah, then we'll do the other side. And this is really important because this, when you do a problem, I was actually using this to help solve it. So say I had this scenario. You can kind of test what would happen if it was one. If you like moved points around, if you move that point kind of closer to it or things like that, does it turn into the infinite wire solution if you do things? If it doesn't, then boundary conditions, yeah. All right, what do y'all say? Okay. Yeah, good. That's the visualization I wanted. That is good. All right, next. What do y'all say? Okay. Yeah, good. All right.
I want to go after
All right, give y'all 20 more seconds because I think we're doing pretty good on this. And then foreshadowing, I'm going to ask what's going to happen to theta 2. That'll be the next question, so you can start thinking about that now if you want. All right, 5, 4, 3, 2, 1. All right, so infinitely far away, what we can basically imagine is as you get infinitely far away, this is kind of my infinite wire, it disappears. This angle, we can see gets smaller and smaller and smaller. Look, this it's kind of hard to see, but imagine that arm gets stretched out to infinity. That angle is going to get flatter and flatter and flatter and flatter and flatter and flatter, such that eventually the angle is 0. Great. All right, let's do the exact same problem, but ask for theta 2. What is theta 2 if the wire is infinite? Now, what's very, very, very important here that I really want to stress to you, this is theta 2, This is not theta 2. That is the mistake that you will likely make on these problems if you make a mistake. Theta 2 is this out angle. It's very easy to accidentally call theta 2 the inwards one. Yeah, a lot of these use sine of the angle instead, and they use the top ones. The problem I run into with that, I guess it's fine. What do you do when the point is off? The wire, that theta 1 currently is defined with respect to r.
Yeah, or you can put the
It's kind of weird. I don't know
So
Yeah.
you're saying we should find like
Off so much wire. I'm fairly confident this equation works if you're off wire. I don't see a reason. Alright, give y'all 15 more seconds. But I'm pretty pleased with the responses. Alright, in 5, 4, 3, 2, 1. Alright, as this wire stretches, that one also gets flatter and flatter and flatter, so that angle gets bigger and bigger and bigger until it reaches the value of pi, 180 degrees. Now, put these pieces together. This is the equation I just gave you for a finite wire. Mu naught I over 4 pi r times cosine of theta 1 minus cosine of theta 2. Just put the values in there, and we're going to derive the infinite wire. Mu naught I over 4 pi r, cosine of 0 is going to be 1, minus cosine of pi is negative 1. 1 minus negative 1 is 2. So we get mu naught I over 2 pi r. 1 minus negative 1 is 2. 2 cancels with a factor of 2 on the bottom. Yay! There's the derivation for an infinite. There's an infinite wire. This does not show up on the formula sheet. This does not show up on the formula sheet. What does show up on the formula sheet? The finite wire. You can make it into an infinite wire if you remember that rule, or put it on your note card. Either or. So I give you the finite wire. Infinite wire derives from that. But that's the solution to it. What if you have a semi-infinite wire where like one end is finite and the other end goes to infinity? Then you just do the same rule. You just figure out your angles. The end that goes to infinity, put the angle that you all have been putting for the side that goes to infinity. I'll straight up tell you the quiz problem that I'm currently making your all's quiz for Friday. One of the problems is find the magnetic field due to this system. It's an infinite wire that bends and then goes upwards. How do we solve this? It's just two wires. It's a finite wire on the bottom and it's an infinitely long on this end. So it's an infinitely long there, but then it ends at this point, and then you have another infinitely long, but it's finite. Anyway, just to show you this, that's theta 1, theta 2 is way over there. Anyway, that's going to test if you really understand it. That's why I made that quiz problem. It's all in variable form. So much fun. All right. Okay. Let's see here. Yeah, we'll do this in the next one, and that'll be good for today. That'll still get us out pretty soon. At some point, B1 equals 3x hat. And at the same point, B2 equals 4y hat. What is the magnitude of the net field? This is to remind you of something you know.
No, my friend
I picked nice numbers too.
Yeah, okay.
It's just to see if you remember if you remember the vectors. Vector in the direction matters.
Five, four, three.
Wait, does he do cars? I don't think we got first.
I just like that there's an extension here, and that's like I don't
All right, 10 seconds. All right, in 5, 4, 3, 2. All right, I'll start chatting about why I leave it open. All right, you got one field that's to the right. You got another field that's up. This one's 3. This one's 4. If you want to add them, you can't just add 3 plus 4. This is something you all know. You've been doing this enough. It's a reminder, though. That's the reason for this problem, was to remind you that if you want to add them, they are vectors. And vectors do not just add. You got to break things into components. So this is going to be 5. Why? Because the square root of 3 squared plus 4 squared equals, 5. Yay. Don't forget that. So when we're doing these problems, we've been fortunate so far that they were always parallel or anti-parallel, but that is not always the case. For example, this one. 2 wires are parallel to each other. So this is the last problem we're going to work on. 2 wires are parallel to each other and both carry a current of 5 amps in the direction pointed into the page. First wire is located at the origin. The other one's 20 centimeters to the right. Find the direction of the magnetic field at some point B that is halfway between the wires and 5 centimeters above the wires. Find the magnetic field at point P. Draw the directions of the... Remember, you always start with the picture and you always draw the directions of the fields before you do any math. Because if you don't know which way these things point, math ain't going to do it for you. Unless you want to do by its smart law. Then it will. Draw your fields. If you don't draw them, you're starting off on a bad place. So what are you going to say the direction the field is? Draw each one independently. So draw the field to the left wire, then draw the field to the right wire. So you do one wire at a time. Then like one doesn't exist. So do the left wire, put your thumb, and remember the field's going to make a circle around it. At point P, which way will that circle point? Yep. So that one's good. So the field. You need it to intersect. Yeah, because your thumb points in. You need to intersect the points.
One to the right and the right one to the left.
So, a couple techniques. Thumb in the direction, and you can either do the circle, or thumb in the direction of current, point your fingers at the point,
going down.
and your palm get to the
Yes,
direction.
yep.
So go ahead and make that line up for the next one of these two. And then you need to make sure your hand is free. You're doing the curl one. So then it's going to make a circle. And the point we care about is
Like not the corner.
draw some dots. Draw circles around. So the magnetic field is going to make a circle.
96.9. What's the
Which way did you make the top of your circle flat. So the other way we can do this is remember you can put your thumb in the section, thumb in the direction of current, fingers towards the point.
Oh, your name is on I think
Just like that.
I know this hard R.
yeah.
I don't know. See if I should work like that.
All right, the key here is doing one wire at a time. Just like when you all found the electric field due to a bunch of charges, you drew the electric field due to each charge, and then you added them all together. Each of these wires is like a point charge. Each one makes a field. Find the field due to each one, and then we'll do the math. So pretend like this wire doesn't exist. This one on the right. Who cares? All right, I got a wire. Find the direction of the magnetic field, some point that's kind of above it to the right. How do we do that? Well, we are going to draw. This would be kind of handy. It'd be helpful maybe to draw some numbers on here. This side is 0.05 meters. This bottom side is 0.1 meters. It's always useful to add those measurements. It's given in the problem. Next, to draw the direction of it. So there's a few options. If you want, you can do the circle one. Remember, magnetic field around a wire is a circle. Now this circle is going to be pretty big. So if we kind of visualize this circle, it's a circle. And what's the direction at that point P? The direction of the circle is clockwise. Why? Right-hand rule. Thumb in the direction of current, spins around. So, at various points it's doing this. So what's it doing at point P? It's going to be going down to the right. That's one way to find the direction, is imagine that circle. The other way is to do the other option. Thumb in the direction of current, fingers towards the point. Which way does my palm point? Down to the right. You get the exact same answer. This palm thing just finds the tangent line. So this one is down to the right. Great. Do the other wire if you haven't done it yet. That's the field due to wire 1. You need to find the field due to both of them. So great, one's down, one to go. And then you just got to use the equation. Well, X and Y component.
That would be that one.
Yeah.
They're both possible. Well, this one is like these point down here.
All right, the other one is going to point up to the right. Oh my gosh, symmetry! We love symmetry. It makes our life easier. We can see here the y components are going to cancel because of their symmetric distances, same current, same distances, all that good stuff. So now the only thing you all need to do is find the value of these, break them into their x components, and combine them together. These are infinite wires, so use the equation for an infinite wire. That's the one that was on the previous slides. And you all need to figure out the angle so that you can break them into x components and whatnot. At this point, the things that you're doing aren't, I mean, I guess you got to find the field using a new equation, but this is just like, every step now that you're doing is just like you did with electric fields. The only thing new here was finding the direction, and the equation you'll use to find the field is new, but it's a very just plug the numbers in and hit enter situation. What's the magnetic field due to an infinite wire? Mu naught I over 2 pi r. Why do I know that? Because I've done a lot of these. In your case, it's on a previous slide. You just grab it. And I'll put the answer somewhere. Yeah, it's going to be really common in these problems saying to find the direction and magnitude. I care about both things. Multiple choice question on the test would just be, hey, maybe what's the direction of the magnetic field? That would be a very reasonable multiple choice question.
They're both going to be theta away from the x point, so I'm just literally doing 2 cosine of the theta times.
Yeah.
That's a lot of writing. I'm going to type more in my calculator than I want to. This is why numbers stink. I didn't have to do numbers. This would be so much quicker.
Are you getting the numerical answer?
Yeah.
Yeah, but then there's 2 pi. Or wait, it's 5 pi.
No.
The angle is 30 degrees.
I think I got 8 e to the minus 6.
The angle is
Oh, so good. Look at that. All right. The answer is 8 e to the minus 6 Tesla to the right. Or 8 micro Tesla. Same answer. You know what? Huh?
A lot.
Is it? No. The Earth's magnetic field, I think, is like to the minus... oh, okay. To be fair, I got 5 amps. 5 amps is a ton of current. I think the Earth's magnetic field is micro.
I thought I was reading your lab like 44 microfarads. So 8 is like a good chunk of that.
The Earth's magnetic field's pretty weak. It's not. No one's really feeling it. You can move a compass.
Super light.
Yeah, it's like a
I did not do the math. Okay, so I can try it.
I just did twice the extra. I think I put something wrong.
I think I was supposed to be
I just did that.
I put 4 pi r instead of 2 pi r. I might be off.
I got some very different.
Yeah,
I think
no.
I screwed up though.
No. I think you might be.
I got 1.6 times 10 minus 5. 1.6 even minus 5.
Yeah, there's a chance that I think I made a mistake here as well.
Yours was 8 micro.
Which I don't know. I know, I still got the same answer. How weird.
Could you not do cosine theta for this?
Yeah, I did 0.1.
0.1 over the square root of the other.
Oh, why do I keep doing 0.5? Yeah. Okay, yeah, I got 1.6.
You did minus 5?
Yeah.
Okay.
All right, correction. I believe it's 16 microtesla.
Oh, so I guess it's just
So if I order
one of the
it's a 30 or a 60 degree,
Yeah.
I think.
Oh, I just did the ratio.
Yeah, I did too. I need more room.
Yeah, they have to get approved, but
All right, there you go. I wrote out everything. All right, so you find the field at each wire. It's mu naught I over 2 pi r. It's an infinite wire. The values are identical. I didn't want to write as much. They're the same I, the same mu naught, the same 2, the same pi, the same r. The value of r, how do you find it? It's the hypotenuse of a triangle. 0.1 squared plus 0.05 squared. Fantastic. The y components cancel because symmetry. You can do it for yourself if you really want and have a great time of it. You know, they both have the same angle, but one's up, one's down. So everything's the same. So in the case of the x components they add, the angle is the same, the b is the same, so I just multiplied it by 2. And instead of calculating the angle by doing cosine inverse, I just put what cosine of theta equals, which is adjacent over hypotenuse. It was a little bit less work for me. You can do that. We've been doing that when we set up our integrals. You don't need to find the angle and then plug in you can just put the definition of cosine theta, which is adjacent over hypotenuse. Put that in there, hit enter, and you should get 1.6 times 10 to the minus 5 Tesla, which is 16 microtesla to the right. Now, somehow, some way, wherever I got this problem from, maybe I typed something different. I don't know, but there was a typo here. I put 8. It should be 1.6. I don't know. I'll have to double check. Yeah, 16. Yeah, so I don't know if it's because I used the finite wire when I was calculating this. That might have been the case. I'm pretty sure I got this from a book, though, so that's why I'm surprised the answer's off. But anywho, the math here is sound. And that's it. What is the takeaway from this problem? What do you at the end of this, what do you take away from it? If you have more than one wire, find the magnetic field due to each wire and add them together. Very likely that it's a really easy free response problem to make, is to make a loop and a straight wire and another straight wire and find the field at some point due to all 3 of them together. You just do this stuff. And there's a bunch of examples of that in the problem set. I got 2 wires here. I got another 2 wires here. I got the 2 arcs here. I got an arc here. I've got a wire with already a known magnetic field. So many of these are just, can you do multiple wires together? That's probably a signifier that it's important to be able to do. If you can do a couple of wires, you can do any. There you go. That's it. All right. Y'all have a good one. Thursday we'll finish up things, get to Ampere's law, do a lot of RC circuits.
It was great.
Big grand time.
Oh my God. Yeah.